Hello, my name is Brian, and today I am presenting a 28 nanometer approximate and binary 6T cam for sequence alignment. My co-authors are Samuel Spitalnik, Muya Chang, and Arijit Raychowdhury. Here's my outline. I'll start with some background and motivation. Next, I'll discuss the design of our approximate cam. And lastly, I'll show our measurements and give a conclusion. So DNA sequencing has become exponentially cheaper, actually outpacing Moore's law, and this is because both hardware and algorithms have improved. 20 years ago, it costed $100 million to sequence an entire human genome, but today it costs only $1,000. And because it's become exponentially cheaper, it's been adopted across new applications in the life sciences because it's now cost effective. The same way integrated circuits are used in applications that you wouldn't have seen them in 20 or 30 years ago because the cost has fallen rapidly. So here's a simple illustration of the DNA sequencing pipeline. First, next generation sequencers produce what are called short reads. These short reads contain sequences on the order of about 100 base pairs. And these sequences are just strings of adenine, cytosine, guanine, and thymine, but from here on I'll just refer to them as ACGT. And the goal of sequence alignment is to stitch these short reads back together, sort of like solving a puzzle where you have a few hundred characters of a billion long sequence. And the good thing is we have good references. So the human genome varies very little between human to human. So you can use one person's genome to help stitch another's back together. Sort of like using the completed picture on the puzzle box as a guide. And this process is still computationally expensive and the major bottleneck in DNA sequencing. And here's a simple illustration for sequence alignment. So again, short reads are on the order of 100 base pairs long, but the human genome is over a billion base pairs long. And so ultimately what we are trying to do is map these short reads to parts of a reference sequence to stitch things back together. And in this example, I'm showing 3 sample short reads and how we are searching for them in this larger reference sequence. And we are using this reference sequence as a guide on how to stitch all the short reads together to reassemble the full sequence. But this idea of searching for substrings in larger sequences motivates the idea to use content addressable memory. Okay, so how might we actually apply CAM to sequence alignment? A first approach with CAM might look like this. So starting on the left with the abstract model, we store the reference string inside the array and apply short reads as input. And so if we input ATC, and the only string that should match is ATC, shown here in the third column. The other 2 strings, CTC and GAG, both mismatch and return 0. And then on the right-hand side, I'm showing a circuit model of this. So we use a 2-bit mapping for the 4 bases. So A is 0, 0, C is 0, 1, G is 1, 0, and T is 1, 1. And then we have a CAM with 6-bit inputs and 3 stored strings. And following the same logic as before, only the third column returns a 1. And so this mapping of sequence alignment to CAM would work great, but there is one caveat here. Sequence alignment actually needs to perform approximate string matching, and this is for 2 reasons. The first reason is that state-of-the-art sequencers produce errors at a rate of 0.1% to 0.5%. And so an error might look like getting a G instead of an A. And then the second reason is that we want to tolerate minor differences because the reference sequence will have differences or variations or mutations from the one we are mapping. And so the solution here is approximate search. And our goal was to design a CAM to do this. So on the right here, I am showing an example of this. We want to say if all the characters in the string match except 1, then it should be a match. And so this is actually computing Hamming distance. Hamming distance here is just the number of mismatching bits between the 2 sequences. And so we're saying if the Hamming distance is less than or equal to 1, return match. And in this example, both the first and third strings match because the Hamming distance is 1 and 0 respectively, but the middle string mismatches because its Hamming distance is 3. And so our goal was to design a CAM capable of efficiently performing approximate search as well as binary search and regular SRAM. At the same time, we wanted to achieve high memory density and good reliability. High density is important here because we cannot store large reference sequences on chip. We saw earlier that this would require gigabytes, but the more data we can cache on chip means the less amount of off-chip memory accesses we need to make. And reliability is obviously important, but especially given that approximate CAM requires multiple states to be encoded in the analog domain, but more details on this part later. Okay, so next I will discuss how we designed the approximate CAM. We started our cam with a popular 6T cam design that has been used in several prior works. Because it is only 6T, not 9T or 10T like typical cams, it achieves high memory density. I'll go through an example on the next slide, but the idea is that you split the word lines of the SRAM into word line left and word line right, and these act as your search lines. And then bitline and bitline bar act as your match lines. So you need two sets of word line drivers for word line left and word line right, and two sets of sense amps for bitline and bitline bar. But with these, you can perform binary cam with a 6T cell. So to split the two word lines, you do have to modify the bit cell, but in N28, it doesn't take any extra area. The bit cell modification just requires changes to the metal layers, where you have to move the two word lines to metal 4. And next, I'll share an example of how 6T BCAM works. So here's an abstract model of BCAM operation where I have a BCAM match and a BCAM mismatch. I'll go through this abstract example first, and then I'll show a circuit model for it. For this example, we have search string 101 and stored strings 001 and 101. And so if we input 101 to our cam, we would expect the first column to output 0, since 101 does not match with 001. But for the second column, 101 matches with 101, and the cam should output 1. Now moving to the circuit implementation, at first bitline and bitline bar are pre-charged just like typical SRAM read, and next the search string is applied to word line left and word line right. So if the search bit is a 1, then word line left is asserted high, and if the search bit is a 0, then word line right is asserted high. Next, if any bit in the search string mismatches with any bit in the stored string, then the corresponding bit line will discharge. So in the top left cell, the search bit is 1, but the stored bit is 0, and so bit line discharges. But in the other column, the stored bit is 1, and so bit line does not discharge. And then to complete the cam operation, we use an AND gate of the output of both sense amps, because if either bitline or bitline bar discharge, then we know it's not a match. So after starting with the 6T BCAM, we already have SRAM and BCAM functionality. To add ACAM mode, we tried several different design ideas, but the one we settled on was a current sense amplifier approach shown here in green at the top of the array. I'll discuss it in detail, but this figure shows the complete view of the cam design. So we have the SRAM array with the pre-charge and write circuits for dynamic read and write. Next, we have two sets of word line drivers and two sets of sense amplifiers for BCAM mode. And lastly, we have the ACAM current sense amplifier 8-to-1 mux and a 6-bit current steering DAC to create a programmable reference voltage. And so over the next few slides, I'll explain how ACAM mode works with some examples. So here is an ACAM operation example where I have an ACAM match and an ACAM mismatch. For this example, a match occurs when the Hamming distance between the search and stored strings is less than or equal to 1. Starting with an abstract example, we input 101 and have stored strings 111 and 110. So in the left column, the Hamming distance between 101 and 111 is 1, and so this is a match and we output 1. In the right column, the Hamming distance between 101 and 110 is 2, and so this is a mismatch because the Hamming distance is greater than 1 and we output 0. But how is this actually implemented? So let's look at a circuit model for this. So just like BCAM, if the search bit is a 1, then word line left is asserted high, and if the search bit is a 0, then word line right is asserted high. Starting with the left column, we input 101, and our stored string is 111. And so the first and third bits match, and so no current is pulled. The second bit mismatches, and so there is a voltage difference across the access device, and so a current is pulled. And this voltage difference is because the internal node here is VSS, but the bit line is regulated to about 300 millivolts. And next, we can move to the second column. Here, the second and third bits mismatch, so two currents are pulled across the sense resistor. And please note here how we can sum current down both bitline and bitline bar over the same sense resistor. Now, it is a bit strange because we are shorting bitline and bitline bar together, but in a few slides, I will show why it isn't an issue for reliability. So what does this regulator look like and how expensive is it? The whole regulator is 4 transistors, and combined with the resistor and compensation cap, the area is 41.12 microns. And adding one to each I/O, or 8 bit lines, costs about 9.2% area overhead. So here M0 is a common gate amplifier, and M2 and M3 are the active load in the form of a cascode current source. The input signal here is the bit line, and the output goes to the PMOS LDO that sources current to the bit cells over the sense resistor. And then using this regulator, each match pulls somewhere between 5 microamps and 10 microamps. And we can control this current using the target bit line and word line voltages. And by increasing the cell current, we can increase power and decrease the voltage headroom, but it improves SNR and reduces errors. So in ACAM mode, there are a few reliability challenges to address. The first challenge is sneak path current. And to illustrate this, I have two circuit diagrams and an IDS-VGS curve. So starting with the mismatch shown by the circuit on the left, here word line is high in the internal node and the bit cell is 0. So the bit cell pulls a current because we have a short from bit line to ground. And this current is given by I pull down or IPD in the plot. But what happens for a match where word line is high and the internal node is 1? This is illustrated by the circuit on the right. Ideally, we want this to act as an open circuit, but depending on the word line and bit line voltages used, it may actually source current. And this condition is represented by I sneak in the plot. So looking at the IDS-VGS curve, we can set the word line voltage to about 500 millivolts and the bit line voltage to 300 millivolts, and then IPD will be greater than 0 and I sneak will be 0, and so that we can avoid the problem of the sneak path current. And a second challenge to address here is noise margin. So shorting bitline and bitline bar is fairly unconventional, but ultimately the noise margin for this operation is higher than regular SRAM dynamic read. I am showing the read noise margin simulation for both SRAM, read, and ACAM mode on the right. And the reason ACAM mode has better noise margin is because we only activate one word line and we set the word line voltage well below VDD. So ACAM mode has two read assist techniques built in. Okay, so the third reliability concern we had was PVT variation in the bit cells during current accumulation, because threshold voltage variation in the pull-down NMOS of the SRAM bit cell will reduce error margin. So to quantify this error, we performed 50,000 searches of sequences 8 characters long and then measured the bit line voltage. So an example of one such sequence is ACTGCTAA. And after collecting the 50,000 samples, we plotted them as a histogram. And so the error is really bad. We have significant overlap between the distributions, and it's not really because of PVT variation, but rather what we call false positives or half matches. And so for the Hamming distance 1 samples, the green ones here, there are 2 different distributions because of the false positives. And so we can actually have a Hamming distance 1 sample and Hamming distance 2 sample give the same bit line voltage, which of course is an error because it's impossible to distinguish between the two of them. And so let's see why this happens. So in our bit mapping, we currently use 2 bits to represent the 4 bases, where A is 0, 0, C is 0, 1, G is 1, 0, and T is 1, 1. And so in the table on the right, I'm showing the Hamming distance between all the base bit mappings. Ideally, we'd want the Hamming distance between any base in itself to be 0, and we would want the Hamming distance between any 2 different bases to be 2, because each base is 2 bits. But that's not the case, so let's see an example. I'm highlighting 2 entries in this table, so the Hamming distance between A and C, and the Hamming distance between A and T. So starting first with A and C, we find our Hamming distance is 1, because A is 0, 0, and C is 0, 1. So the first bit matches, but the second bit mismatches. And next, the Hamming distance between A and T is 2, because both bits mismatch. And so although the Hamming distance between A and C and A and T should be equal, it's actually different because of the 2-bit representation. And next I'll show why this problem can be solved by using gray codes. So gray codes are a different type of coding where the bit string should only change 1 bit between 2 consecutive numbers. But we can extend this idea by making it so exactly 2 bits change between any 2 bases. And this will solve our problem from before by guaranteeing that the Hamming distance between any 2 different bases will be 2. But to do this, we need to use 3 bits per base. And so following this idea, our bit mapping will be A is 0, 0, 0, C is 0, 1, 1, G is 1, 1, 0, and T is 1, 0, 1. And if we reconstruct our table with the 3-bit gray codes, we'll see that all the bases have a Hamming distance of 2 between them. And looking at the same 2 examples from before, we can see that the Hamming distance from A to C is 2, because A is 0, 0, 0, and C is 0, 1, 1. And the Hamming distance from A to T is also 2, because A is 0, 0, 0, and T is 1, 0, 1. So now, if we recollect our experiment, we should find that the problem of false positives is gone. And so next we reran the experiment using gray codes, and the results look much better. So we again ran 50,000 searches and measured the bit line voltage. And we found that the half matches are gone, so each Hamming distance directly maps to a single outcome in the histogram. And although we have some PVT variation, the gray code has given us an extra LSB of precision because now the outcome has a Hamming distance of 2 from each other, not just 1. And so we find that we can achieve 5 sigma separation for the Hamming distance 1 condition and about 4.4 sigma for the Hamming distance 2 condition. And this, of course, gets worse for Hamming distance 3, 4, and so on. But we don't really care much about these because for our application, we're interested in strings that mostly match. So maybe just 1 or 2 mismatches. So here is the PCB and test chip. It is fabricated in a 28 nanometer process. The total chip area is 2 millimeter by 2 millimeter, but we only use the bottom 2/3 or so for this design. And I've outlined the 3 major components, so the SRAM, the CAM, and the CPU. And it operates up to 200 megahertz and from 600 millivolts to 1 volt. To test the CAM and use it in real programs, we embedded 16 CAM instances to a RISC-V CPU with the 4 megabit SRAM. Next, we added a few custom instructions so we could use the CAM as part of the data path instead of memory mapping it. And we also created a custom C-Lite compiler to use these instructions. And I won't go into any more detail about the CPU because the focus of this work really was the CAM. So here's the CAM's area breakdown and layout. So we achieve a memory efficiency of 56.5%. So 56.5% of the area is bit cells alone. We achieve a memory density of 2.54 megabits per millimeter squared with logic rule cells. And we could have used push rule cells, but the Foundry SRAM didn't come with a simulation model, so we chose to use logic rules instead. But had we used push rules, we would have gotten 3.32 megabits per millimeter squared. And the current sense amplifier occupied only 9.2% of the total area, but I think that this could have actually been a lot smaller. Here is the shmoo and voltage versus frequency plot. So BCAM operates from 600 millivolts to 1 volt, and ACAM operates from 700 millivolts to 1 volt. And the reason for the difference is because in ACAM mode, extra voltage headroom is required to keep all the transistors in the regulator in saturation. But even at 700 millivolts, ACAM is really slow, and so the best figure of merit is achieved at 800 millivolts. For those unfamiliar, the figure of merit for CAM is typically given by energy per search per bit. So basically, on average, how much energy did each bit comparison cost? For BCAM, we achieved 0.77 femtojoules per search per bit, and for ACAM, we achieved 2.37 femtojoules per search per bit. And in ACAM mode, it's higher because it pulls a DC current, and it also requires a higher operating voltage. Okay, and wrapping up, here is a comparison table with prior work. We found it a bit difficult to make a comparison because there were no approximate CAMs we could find published with measured data, just simulations. So we compared against classical CAMs. And so for the BCAM operation, our design lags behind the classical CAMs because we used a mux ratio of 8 to preserve memory density, while the other designs had a mux ratio of 1, so no mux. We have good memory density, so almost as good as the original 6T BCAM paper, despite having the overhead of a current sense amplifier. But our design performs about 11 times better than the closest possible BCAM at approximate search. And the way we approximated the ACAM figure of merit for BCAMs was by computing the number of BCAM operations that would be required to implement the same ACAM operation. And so in conclusion, sequence alignment requires approximate string matching, and thus classical binary CAM is not sufficient. So we propose a approximate string matching capable 6T BCAM or 6T CAM achieving 0.77 femtojoules per search per bit in BCAM mode and 2.37 femtojoules per search per bit in ACAM mode. Our design achieves a high memory density of 2.54 megabits per millimeter squared using logic rules, and we overcame 3 potential reliability concerns in the form of read noise margin, sneak path current, and device-to-device variation. And lastly, we integrated our CAM into a RISC-V processor for sequence alignment. And with that, I will end my presentation and take any questions from the audience.